let's start this. So thank you very much, everyone, for joining us. Thank you, Mélanie, for joining us to give this talk today. So Mélanie received an MSc degree in general engineering from Lyon, and has since then mostly been at DTU, I believe, in Copenhagen, where she's also worked with Saint-Gobain Ecofon in their research department, and has done this really interesting work that has all manner of applications. I think in looking at isotropy in reverberant spaces. So this has started off looking at reverberant rooms, but I think there's a whole manner of possible applications. I've got two people here actually today who just said hello, looking at reverberant testing for aerospace, for example. So there's some other possible applications too. It might be exciting. And Mélanie herself currently has a fellowship and is off to America, I think, to work with Peter D'Antonio and Nin Xing, looking at some planar scanners. So I don't know if you are going to tell us about that today or not, but over to you. Thank you very much.
Thank you very much, and thank you very much for inviting me. I'm very pleased to give this seminar. So I guess you did the introduction, but yeah. So I'm currently a postdoc between DTU and the Laboratoire d'Acoustique de l'Université du Mans in France, and I'll be off to the US from September as part of the Hunt postdoctoral fellowship from the Acoustical Society of America. So my main research interests are in sound field analysis, array processing, with a topic of predilection in measurement of sound absorption. So that's what I'm mostly going to talk about today. So of course you're all familiar with this, but very briefly, sound absorption. So we have when we have an incident wave on a surface that gives so part of its energy will be reflected back into the room, part of it will be transmitted through the wall, and the rest will be absorbed and transformed into heat into the material. And the amount of energy that's being absorbed depends on the absorption coefficient of the material, which is defined as the ratio between the absorbed energy and the incident energy. So of course, knowledge of absorption coefficients of typical building material is of importance for all tasks related to room acoustical design, and also to get reliable predictions, numerical predictions of the sound field in a room. So the way it is usually measured, so the most common way these absorption coefficients are measured is in the reverberation chamber, so according to the ISO 354. And in this standard, a large sample of the material is placed in the room, and the absorption coefficient is deduced from the reduction in reverberation time when the sample is placed in the room, based on a Sabine formula. So the basic idea behind this method is that because we cannot measure absorption directly, we make use of a mathematical model, so in this case the reverberation theory, to deduce the absorption coefficient from a simple measurement of the sound pressure. And as you know, this reverberation theory assumes a diffuse sound field, so a sound field that is totally homogeneous and isotropic. And because of this assumption, the absorption coefficient that's measured in the chamber is average over random angles of incidence. So sound is considered to strike the sample equally from all directions. So it's quite easy to see already that these assumptions, so a diffuse sound field and isotropic sound incidence on the sample, will not be verified in the reverberation chambers. So the reason is that when we place a single concentrated sample of absorbing material on the floor, this will favor the separation between a grazing sound field that propagates in the plane parallel to the absorber and that will be slowly decaying, and a non-grazing sound field that will be very much absorbed by the sample. And of course, then the sound field will be fairly directional and cannot be nor diffuse nor isotropic. And in fact, when we measure the same sample of absorbing material in different labs, what we see is that we have very different results. So these are the results from a round-robin test I did back in 2014, where I visited 7 European labs with the same equipment and with the same sample, which is in fact the reference absorber that's now discussed for the revision of the ISO 354. And as you can see, it's hard to tell what is in fact the absorption coefficient of this sample. And the reason for this, or at least what we hypothesize, is that all these absorption curves are measured in different sound fields, none of them being diffuse, and all of these sound fields are non-diffuse in very different ways. Now, how do we measure or quantify how these particular sound fields deviate from a diffuse sound field? That's something that we haven't been able to measure so far. And I just want to draw your attention to the fact that this is not a new problem. So I have here a quote from Hunt at the 10th anniversary meeting of the Acoustical Society of America in 1939, where he says that the existence of an absorption coefficient problem 10 years ago provided one of the motivating influences which, in 1928, drew together the group of men who founded the Acoustical Society of America. It should not require many words on my part to convince you that we still have a problem on our hands. And I would say that almost a century ago, we still have the same problem. It remains unresolved. So in this seminar presentation, I'm going to address the following questions. How does the sound energy distribute itself within a reverberation chamber? And how do specific sound fields deviate from the state of diffusion? We'll see what we can actually give a measure for sound field diffusion. We will also look into how does the sound incidence distribute itself on the measuring sample. And finally, we will question the use of a random incidence absorption coefficient in rooms where losses are mostly dominated by specific angles of incidence. So that is in most ordinary rooms, in fact. And we'll see that it seems more appropriate to use angle-dependent coefficients instead of random incident coefficients to better account for the energy dissipation at the boundaries. And we will see how, based on the framework that I will present here, we can obtain this type of data. So just a little bit of historical perspective on the measurement of sound diffusion. So obviously over a century there's been many methods proposed, which I'm not going to cover, but among these methods, maybe the most meaningful way of looking at diffusion is to define it based on the angular distribution of sound energy. So with the idea that if the sound field is totally diffuse, the distribution of sound energy will be equal in all directions. And so the first attempt to actually measure these directional properties in reverberant sound fields is due to Meyer and Thiele, who measured the directional properties and the angular distribution of sound energy in concert halls using a concave mirror and a directional microphone. And then they presented the data in the form of these sound hedgehogs that basically show the direction and amplitude of the arriving waves. But it's not, so it's in fact as early as 1959 that a microphone array, the use of a microphone array was suggested by Schroeder. So he suggested using a microphone array by sampling the sound field on a measuring wall of a reverberation chamber in order to look at the distribution of sound incidence on the wall. Unfortunately, he only presented the theoretical foundations of the experimental method, but no results were presented. And it's not before 2004, sorry, went too fast, 2004 that Gover introduced or looked into the use of spherical microphone arrays to measure the directional properties of sound fields. So instead of using a single microphone that is rotated manually in all directions, as Meyer and Thiele did, he used a spherical microphone array to adapt that same method and steer beams in every directions. So the method that we propose here is basically based on the same line of ideas, in that it sees sound field diffusion in terms of the angular distribution of sound energy, but this time in the plane wave expansion of the sound field. So here I'll be talking about isotropy, mostly because we look at the angular distribution of sound energy. So the basic idea behind this method is that we can express the sound field measure at a point in a room as the superposition of plane waves. So that is basically just applying a 3D Fourier transform to a measured field and basically look at the problem in the spatial frequency domain. And if we are far from the boundaries of the room and we're far from sources, then we can assume that these plane waves are propagating waves. And each of them is traveling with a direction given by the wave number vector k, and may have different amplitude and phases that we account for by using this p coefficient, capital P coefficient, which is in fact the wave number spectrum. And now, if we distribute the basis of elementary wave over a spherical domain, we can recover the directional properties of the sound field based on the magnitude of the wave number spectrum. So it could look something like this, where here we have a single propagating wave, and that give rise to a local maximum on the wave number spectrum representation. I just want to draw your attention to the fact that with this convention, the wave number spectrum represents the direction of propagation of the waves and not the direction of arrival. So, of course, if we want to calculate these P coefficients, we need more than one equation. So, therefore, we will use array measurements. So, if we measure the sound field at multiple points in the room, we can obtain a system of equation that we can write in matrix form in the following way, where P is a vector of measured sound pressures, H is a transfer matrix containing the plane wave functions, and X is a complex coefficient vector containing the wave number spectrum coefficients that we want to solve for. So usually this system is underdetermined because we have less measurement points than we have waves in the plane wave expansion. So it requires regularization, but I'm not going to enter into this in this presentation. So how do we use this now to quantify isotropy? So we can start from the observation that if a sound field would be fully isotropic, so waves incoming from all directions, so that's the case on the left-hand side, then the wave number spectrum magnitude would be a constant over a sphere. And in the opposite case of a single propagating wave, then the magnitude of the wave number spectrum will basically resemble a Dirac delta function on the sphere. So that gave us the idea of exploiting the properties of the spherical harmonic functions and the spherical Fourier transform to quantify isotropy. So the idea is that we expand the magnitude of the wave number spectrum in a spherical harmonics basis, so using the spherical harmonics as basis function. And then we say that if the sound field is completely isotropic, then this magnitude of the wave number spectrum will be best described by the monopole moment only. And as soon as there is a degree of asymmetry in the sound field, we will need other moments to describe this wave number spectrum magnitude. And so these are basically simple properties of the spherical Fourier transform. And based on that, we define what we call an isotropy indicator. which is basically the relative strength of the monopole moment. And that's a number between 0 and 1. 0 if the sound field is anisotropic, and 1 if it's fully isotropic. So of course, it's difficult to validate this method against objective measures of the isotropy in the sound field. So what we did to check the sensitivity of the method, yes, sorry, it went too fast again. So what we did to check the sensitivity of the isotropy indicator was to try the proposed method in different sound fields of expected increasing isotropy. So we start with the simple case of an anechoic chamber with a single source. Then we'll have a reverberation chamber, in which we have first placed a sample of absorbing materials, and then the empty chamber. And finally, we have 52 loudspeakers organized over a spherical domain in an anechoic chamber. So I'll go through some of the results. So starting with the single source in the anechoic chamber. So you have here on the right hand side the magnitude of the wave number spectrum at 500 Hertz and the corresponding spherical harmonic expansion. And we can see that all of the moments are required to describe this wave number spectrum magnitude, indicating that the sound field is strongly anisotropic, and in fact the isotropy indicator in this case is 0.02. Here we have some results in the reverberation chamber. So it's a chamber that conforms the requirement for ISO 354. It contains 85 built-in boundary diffusers and some additional panel diffusers. And we've looked at the room both in the empty condition and with added absorption on the floor, so as would be in the ISO 354 configuration. And here you have a comparison between the wave number spectrum magnitude in the empty chamber and when absorption is added on the floor. And we can see that in the empty room we have some dominant directions of propagation due to the source and some early reflections. And on the right hand side, in the situation with the absorber on the floor, we see that the field seems less omnidirectional, mostly because there is nothing propagating in the Z positive direction, as nothing is being reflected back from the absorbing plane. And now, if we look at the corresponding spherical harmonic expansion, so that's on the left hand side, we see that in the empty room the monopole moment seems to dominate somewhat the spherical harmonic expansion, leading to an isotropy indicator of 0.67, yet it is clearly not fully isotropic. And then in the situation with the absorber, the monopole moment no longer dominates the spherical harmonic expansion, and we go down to 0.35 for the isotropy indicator. Then in the middle graph you have the isotropy indicator as a function of frequency. So here it's easy to see that the sound field in the damped room is less isotropic than in the empty room. But what's mostly interesting is that so I've put for what it's worth, I've put the ISO 354 measurement of the absorption coefficient of the sample. And we see that the isotropy indicator seems to follow the trend of the absorption. So towards high frequency, when the absorption is increasing, the isotropy indicator is decreasing. Yes, and then finally some measurement in the anechoic chamber with the loudspeaker array. So it's a loudspeaker array of 52 sources that are distributed over a spherical domain surrounding the spherical array. That's maybe something I should have said in the beginning that we are measuring all of these sound fields with a rigid sphere, a rigid spherical array with 64 microphones. And we did that at that point of the research because that equipment was available. But we will see in the rest of the presentation that the method is not does not require any specific array configuration. But in this case, we use the spherical array. And so I was saying that we have this loudspeaker array around the sphere, and it cannot be seen on this picture, but we also actually have loudspeakers below the suspended floor of the anechoic chamber. And these sources are run with uncorrelated white noise so as to mimic diffuse sound field. And so we have here on the right-hand side the wave number spectral magnitude, which seems pretty constant over the spherical domain, and the corresponding spherical harmonic expansion at 125 Hertz, yielding an isotropy indicator of 0.91. So all in all, I'm just recalling here the numbers that we've seen. It seems that this indicator is sensitive, and we're able to measure the degree of diffusion in the different rooms. So now we've been looking mostly at steady state, what happens during the decay. So when we measure the absorption coefficient with ISO 354, we need to have a diffuse sound field both before and during the decay. And we can expect that the wave number properties will change over time. So we need a time-dependent wave number representation to be able to look into the changes in the sound field structures over time. And if we get this sort of representation, then we can easily look into the directional properties both in space and time. And that can be done pretty easily based on a short time Fourier transform that you have here in its classic sliding window form, where this PW is the discrete Fourier transform of the short time section P times W. And then for each time window, we can expand this discrete Fourier transform into a plane wave basis so as to obtain the coefficients P, so the wave number for each time window, so giving a time-dependent representation of the wave number spectra. And then obviously for each of these wave number spectrum, we can apply the spherical harmonic expansion and look at isotropy over time. So we did some measurements again, this time in a different reverberation chamber, a bit larger, in 4 configurations. So the empty room, no absorber, no diffusers. Then the empty room with 19 panel diffusers. Then we've added a sample of absorbing material, and we looked at the room without diffusers and with diffusers. And this time we didn't use the spherical array or the rigid sphere, but we used a scanning robot to create a sequential array of about 300 positions. And in this case, those positions were distributed over 2 concentric spheres. So I have here a little video showing you the evolution of the wave number spectrum in the case with absorber, without diffusers on the left and with diffusers on the right. So I will run it in loops. What you should be so I just want to draw your attention to the fact that, again, the wave number spectrum is defined as to show the direction of propagation of the waves, so that the incident field on the sample is mostly seen on the lower hemisphere of the spheres. And what is to be observed here is that you will see that when we have diffusers in the room, the sound field is a bit more omnidirectional. And what's mainly interesting in the left-hand side, towards the end of the decay, we see some persisting tangential and axial modes, so waves propagating back and forth in between the side walls of the room in the plane parallel to the absorber, and that are not being absorbed, or that are being absorbed at a slower rate than the rest of the sound field. So I'm going to try and play it. Let me know if this is not working. So here towards the end, you can see the tangential field on the left-hand side. Yeah. So, yes. And now looking at the isotropy indicator over time, so these are results presented at 500 Hertz. So in the 4 different configurations. First of all, what we see is that, as expected, the empty room is more isotropic than the room with the absorber, although not fully isotropic, even in the empty room with diffusers. So a fully isotropic sound field would reach a value of 1. And then maybe we can look at the lower black curve that corresponds to the damped case without diffusers. And there we can see that initially, so at time 0, when we're still in steady state, the sound field is very much anisotropic due to the source and due to the few early reflections that dominate the sound field. And then initially we see an increase in isotropy because this direct field and early reflection disappear, and the later reflections serve to build up the sound field in a way that increases the uniformity on the wave number spectrum. And then finally we see that this increase is followed by a slight drop in the isotropy because the sound field is becoming more and more directive, as we could see due to these axial and tangential modes that persist and are not being absorbed or at a slower rate in the room. Yes, so now what we've been looking at is isotropy at a particular location in the room, so around the array. And in that sense, we are not analyzing the compliance of these rooms with ISO 354. So to do that, we would need to conduct extended measurement. And we could do so, for instance, using this sound field analysis recorder that was suggested by Peter D'Antonio, who calls it a SOFAR. So that's an equipment that I've been working with Peter into developing, and it consists basically of 32 microphones that can be automatically moved in 4 parallel planes above the sample, and that will scan the entire testing area. So we can, with this apparatus, we can measure a little more than 4,000 impulse responses. That should allow us to quantify isotropy in the entire testing area. So far the SOFAR is in place in the Acoustical Research Center at RPG, but we couldn't conduct measurements yet due to the COVID-19 pandemic. All right, so now let's see how we can, I guess I still have a little bit of time. Let's see how we can look at how the incident field distributes itself over the sample based on the same framework. So it's pretty similar. In this case, we will simply measure in the close vicinity of the sample, and when we do that and we expand the pressured field into plane waves, then we can actually separate the contribution of the reflected or the waves that conform the reflected field and the waves that conform the incident field. And obviously, looking at the distribution of the wave number spectrum in the incident part of it, we can see how isotropic is the sound field there. Another interesting thing that we can do with this is that we can extrapolate the sound field or reconstruct the sound field at other points than the ones that are measured in order to reconstruct basic quantities, so pressure, particle velocity, intensity. And we can do that either using the whole wave number coefficients, so as to reconstruct the total sound field, or just use the incident part of it so as to reconstruct the incident sound field. So I'm going to show you a few results regarding this. So first of all, some wave number spectra. So we did again measurements in a reverberation chamber, empty, and we've added absorption on the floor, and we used again this scanning robot. This time we didn't use spherical array, it's a sequential array with 290 positions that are randomly distributed within the rectangular volume in the vicinity of the sample. And here an example of 1 kilohertz. So what you should look at is it's in the red rectangle, that's the incident field. And we see that we have some dominant directions in both cases, in the empty field and in the in the damped room. So none of them is isotropic as expected. But what's maybe most interesting is to see that the incident field is different in both situations, meaning that the sample itself has an influence on the incident field. And then looking at some reconstruction of intensity in the domain on top of the absorber. So here you have the net intensity, so that's the total intensity field. So on the left-hand side in the empty room, on the right-hand side with added absorption, and we have both the active and reactive intensity. So if we look first at the empty room, we see that the active intensity is basically flowing in random directions, and that we have more or less the same, we have the same magnitude for both the active and reactive field. But when we look at the damped room, then we see that the sound field, first of all, is mostly active, and we see this strong flow of energy directed towards the sample with a slight curving from the direction of the source. And then we have a very weak reactive field, but interestingly, we see that this reactive field is actually located in the XY plane. It's going back and forth in the XY plane, meaning that we have standing waves in that plane, but we do not have standing waves in the Z direction, and instead we have a flow of energy. So that is all in agreement with what we would expect from theory. And here, finally, for the first time, we've been able to reconstruct the incident intensity only on the sample, and what we can see here is that it's not completely homogeneous, which would be the case if we would have an isotropic sound field. But then, of course, I should remark that the incident intensity cannot give us information about the directional properties of the sound field, as opposed to the wave number spectrum, because intensity is usually due to several interfering waves. but at least it can give us an indication regarding whether or not the sound field that we're measuring departs from the assumption of a perfectly isotropic or diffuse sound field. Yes, and the last thing I want to talk about is the estimation of an angle-dependent absorption coefficient based on this sound field separation. So we can define this absorption coefficient where the numerator is the reflected power and the denominator is the incident power. And it's easy to see here from this formula that the absorption coefficient could be singular in cases where we have no incident energy, so if the denominator would be 0. So what we do is that we average over azimuth angle to ensure that we have a finite amount of energy incoming from all directions. This method, for those who are familiar with the literature, is quite similar to the Tamura method, with some improvements. So in the sense that in this case we are not operating in the near field over a planar surface, but we're actually sampling the sound field over a three-dimensional volume to better resolve the 3D space. And we are solving the amplitudes of the waves by regularized inversion and not a Fourier transform, which allows to circumvent errors due to the finite measurement aperture. And finally, because this absorption coefficient is derived in the Wavenumber domain, the 3D Wavenumber domain directly, we can actually infer the angle-dependent absorption coefficient for all angles of incidence simultaneously with one source position. So the method can be adapted to a situation where we are in a reverberant field. Here is some results from the same set of measurements as before in the reverberation chamber, where we have placed this 100mm glass wool on the floor. And we compare here the measured absorption coefficient to a simple theoretical prediction based on a transfer matrix method, where the porous layer is modeled using a Mickey model, and we see that we have fair agreement. And lastly, I'll just show you some results in a bit more complicated case. So it's a suspended ceiling in a classroom. So it's 20mm glass wool backed by an air cavity. I have here an example of the Wavenumber spectrum at 630 Hertz. But mostly what's interesting is the absorption coefficient that can be recovered, the angle-dependent absorption coefficient. So here for selected frequencies, we can see that apart from the cavity modes, we recover the general trend as compared to theory of this absorption coefficient. Yes, so that is basically all for me. I would like to, if I can, yes, I would like to thank my collaborators on this work, and I leave here the reference to the published papers if you need more information. Thank you very much for listening.
Thank you very much. Interesting. And 2 jars of covers. I said 1 jar of cover in my publicity, but it's actually 2. Even better. Thank you very much. I think that's personally, I think that really brings this whole kind of field to life, because we talk about diffuse fields in this kind of abstract mathematical way. You know, sound from all angles. We know that that's a mathematical idealization. We know that real rooms don't behave totally like that. And I think this is, you know, quite just captures visually sort of beautifully the actual things that do occur in real rooms. So I think that's really exciting.